Welcome back to Chapter 12 on nervous tissue. This is going to be part 2. So now that we've become familiar with the nervous system and we can tell the difference between the central nervous system and the peripheral nervous system, the difference between a neuron and a neuroglial cell, as well as the different types of glial cells, let's go ahead and take a look at the production of the action potential or the excitement within the nervous tissue. As you may recall from our histology section, something that sets the nervous tissue as well as the muscular tissue apart from the other tissue types is the fact that they're able to be electrically stimulated and produce a response. In this case, when we take a look at the nervous tissue, the response will be a signal that will be sent down the axon to make a synaptic connection. This is all based on the fact that when we look at the living cells within the nervous tissue, the cell membranes are what we call polarized. Polarized means that very similar to a battery, they're able to carry a charge. And it's due to the fact that there is an unequal amount of electrolytes, primarily sodium and potassium, when you compare the extracellular fluid, so what's happening outside of the cell, to the intercellular fluid, what's happening on the inside of the cell. Now, it just so happens that the cell membrane is permeable to the different ions. In fact, if we were comparing the two main ions that we need to discuss whenever we look at a polarized or an excitable cell membrane, we would be discussing potassium and we would be discussing sodium. And we see that overall the cell membrane tends to be very permeable to to potassium and less permeable to sodium. So once again, my apologies, very permeable to potassium, less permeable to sodium. Now your body will spend a lot of ATP to maintain the sodium-potassium pump, and this pump is embedded within the cell membranes, and what it does is on a continuously basis, it regulates how much electrical current is being displayed through the cell membrane, and it does so by pumping out 3 sodiums for every 2 potassium ions that it allows to enter inside of the cell membrane. So this continuous exchange of sodium and potassium requires a lot of ATP, a lot of chemical energy, but is extremely essential to maintain what we like to call the resting membrane potential and also make it easy for the cell to get excitable when it's properly stimulated. Here on this illustration, what we're seeing is we're looking at the extracellular fluid, so what's happening on the outside of the cell. This is the intracellular fluid on the inside. We can see our little cell membrane right over here, and then embedded within it we have our sodium channel in orange and our potassium channel in blue. Now go ahead and take a look at the written aspect on the right-hand side of the figure, and what we're going to see is if we compare the concentration, we could see that there's a lot more sodium on the outside of the cell than there is on the inside of the cell. Potassium is going to be the opposite. You're going to have a lot more potassium on the inside, because remember the cell is very permeable to the potassium, so the potassium has an easier time coming in, than it is on the outside of the cell. And because these sodium and potassium ions carry a charge, they are able to help polarize the cell membrane. So by manipulating the quantity of sodium and potassium that I have either inside or outside of my cell, I can regulate how positive or how negative my cell membrane is going to be. And that's then the basis of what we're going to see when we talk about exciting the cell membrane and doing something called inducing an action potential. So here the cell membrane is at resting membrane potential, meaning that the cell has regulated how much it wants on the outside and on the inside at rest. So the cell is just resting. It has not been induced or stimulated to give a response just yet. Now, what goes into creating a response for a cell? Well, in order to do that, we're going to have to manipulate the voltage, the membrane voltage, or the charge that comes across a cell membrane. Basically, what we're going to need to do is we're going to have to make the cell membrane more positive for it to get excitable and for it to send its signal. And once that signal or that response is sent, we need the cell membrane to come back down to its resting membrane potential. So we need it to come back more negative so it can lower its membrane voltage. Now, we're going to see different diagrams at different times, but for now what I want you to do is I want you to take a look at the little diagram that's inserted right over here on the right-hand side. And I'm actually going to be increasing it on the next slide. But basically what we see happening here is that the book, or the PowerPoint, mentioned to us previously that there's a resting membrane potential. So this is the natural charge that goes through the membrane when the membrane is at rest. And as you can see, it's about negative 70 millivolts. And remember, this charge is all due to the imbalance between the sodium and the potassium. Now, if we want to go from resting membrane potential to action potential, and action potential, think of it as excitability. This is when I'm sending my signal. So you're stimulating the cell. This is when the cell is responding to that stimulus. In order for us to go from resting membrane potential to action potential, notice how the voltage has to increase. The cell membrane has to become more positive. And that process of becoming more positive is called depolarization. So anytime you see the word depolarization, I want you to think about the fact that I am increasing my membrane voltage. So I'm making my cell membrane more positive. Now, how am I going to do that? Well, I'm going to rely on sodium to come into the cell. So sodium will enter the cell, and as a result, as sodium comes flooding into the cell, the membrane is going to notice it. It's going to become more positive, and we call that depolarization. At a certain point, all your channels of sodium are fully open. And when that happens, then you have your peak. You cannot get more positive than this. So then what we see happening is once the sodium is done, the sodium channels will close. And then we see the membrane starts to go back down. Right? You see how it's starting to go from positive 35 back to negative 70 millivolts. The decrease in membrane voltage is called repolarization, as in resetting itself. And this is going to be due to potassium. Potassium has to exit the cell. And as it leaves the cell, it lowers the membrane voltage, thereby allowing you to go back to resting membrane potential. Now notice on your little chart by the resting membrane potential, notice how when you get to number 6, you see how the red line slightly dips below the dotted black line that's meant to represent the negative 70. And the reason for that is because since the potassium ions are more permeable, they will quickly escape out of the cell membrane, which means that the cell will slightly become more negative than it needs to be. So see how it dips below the negative 70? So this dip is called hyperpolarization, and it's usually quite normal at the end of repolarization, and it can quickly be adjusted by closing off the potassium and then once again waiting for the sodiums to open up so you can once again do your whole depolarization step. Now, another thing I want to point out to you, and once again I'm going to show you this graph a little bit larger, we're going to do it all over again, is notice that they've also indicated for you that you have a threshold. So the threshold is basically the minimum amount of stimulus or the minimum amount of increase in your membrane voltage that is required before an action potential can be done. So this is like an all or nothing situation. When you start opening your sodium channels, they slowly start coming into the cell and it slowly starts moving the membrane voltage up. When it gets to negative 55 millivolts, that is then when you've reached your threshold. That's the minimum amount you need to get excited to give a full response. And in that case, we'll see that all the sodium channels open up, and that's why you then have that high spike up to positive 35 millivolts. Now, the whole movement of going up and down, depolarization and repolarization, is all part of an action potential. So once again, when you see an action potential, I want you to think that I'm exciting the cell so that it can respond. And by exciting it, that means that I increase its membrane voltage. I make it more positive, depolarization. And when I'm done, I'm going to bring it back to where it was. So I am going to make it more negative, and that's going to be my repolarization. And that is going to be for potassium coming out of the cell. You know what? Let's flick over to the next slide. Here is the picture all over again, and let me tell the story again, and let's see if you're comfortable with the material, okay? Also, keep an eye on the different key terms as I'm going through, so let me make sure I cover everything. Okay, so first things first, you have a resting membrane potential. And that basically indicates the potential that you have an electrical current that runs through the plasma membrane. It is due to an imbalance of sodium and potassium. Negative 70 millivolts is what we're looking at. Okay, that's our membrane. Now, if we want to excite the cell, we're going to go ahead and we're going to open up sodium, Na, and we're going to get the sodium channels to pump sodium into the cell. And it's going to keep pumping it until it gets to the threshold, meaning there's no going back now. So we're going to open up all the sodium channels, more than we can think of, and it's going to increase the membrane voltage. That is going to be depolarization at its best, meaning you increase the membrane voltage, and this is because sodium is entering into the cell. At a certain point, you peak. You have reached your action potential. The cell was excited, it responded. So now what we need to do is we need to go back to where we began. So we're going to have to lower the membrane voltage back to where we started. And in order to do that, we're going to do repolarization. Repolarization, as in resetting, means that I'm taking my potassium ions and I'm kicking it out of the cell. So as I'm kicking it out of the cell membrane potential plummets down, and because potassium is so permeable, we're going to have a slight dip where we go below the value we need to be. We're going to be a little bit more negative than normal. That's called hyperpolarization. That will quickly restore itself back to the resting membrane potential when the potassium channels close, and then we just kind of sit there waiting for the next stimulation so that sodium can enter. And as sodium enters, once again we do our depolarization, we reach our action potential, and then we repolarize or reset by allowing potassium to come out of the cell. For your exam, please be able to tell me that depolarization means an increase in membrane voltage, and it's because sodium comes into the cell, whereas repolarization is when you decrease the membrane voltage, so the cell becomes more negative, and that's because potassium is coming out of the cell. And also, obviously, what resting membrane potential indicates, what the threshold indicates, and what hyperpolarization indicates. Now, once you have the cell primarily excitable and it's done its action potential, it turns out that there will be a refractory period. A refractory period is basically an amount of time where the cell cannot be excited because it's already in the middle of the process of doing an action potential. So we like to think of it as resistance to stimulation. So you can keep stimulating the cell, but it won't respond to you because it's already responding, or it's in the process of kind of resetting itself. So what we have is we have an absolute refractory period, and you have a relative refractory period. The absolute refractory period is right during the time that the action potential is occurring. So notice here in like the pink colored column, notice how the absolute refractory period takes up the same time that we do for us to do our depolarization, action potential, and repolarization. So the cell is already in the middle of responding. All the sodium gates are open. So regardless of how much stimulus we add to it, we can't generate another action potential on top of the one that's already going on. Okay? So an absolute refractory period basically means no matter how much stimulus you add, you will not get another action potential because you're already in the middle of your first one. Then you have a relative refractory period indicated by the yellow column right here. This one is going to be occurring during the part where we do our hyperpolarization and we're resetting over to the resting membrane potential. So at this point, what we see happening is that the potassium gates are still open, so your membrane has a tendency to become more negative. And what we want to do is we want to have it go back up to be more positive. So we want to redo the whole depolarization, action potential, repolarization. In order to do that, we're going to have to force the potassium channels to close so that the sodium channels will open up and we can go ahead and increase our membrane voltage. In order to do that, we're going to need a really strong stimulus. So a really strong stimulus will be the only way that we can go ahead and cause a reaction during the relative refractory period. All right, and what we see happening is that the refractory period basically hobbles or follows right behind the action potential as it's making its way down the axon within the nervous system. So here, for instance, I have my little axon. Notice how the signal is moving down. We're doing anterograde. Even when you look at the little inserts right here, this is basically just showing you the part of the axon. And notice when you take a look at the color code of the cell membrane, you have your excitable membrane in green, which you can see the whole thing is excitable. Then in pink, you see that this is where an action potential is occurring. So these groups of cells, or this part of the cell, is responding to your stimulus. But the action potential doesn't stay there long. It's quickly going to start moving down the axon. So you see how the axon is, and then notice how the pink moves one spot over as you look down at the illustration. So it's basically going ahead and taking a look at producing an action potential on the excitable cell. And look behind the color code of the pink. You have a little yellow area. The yellow area is the refractory period, or the refractory membrane, I should say. So this is the time that the students have to kind of reset themselves real quick and get ready for a next set of stimulation. All right? So the refractory period follows right behind the action potential. Now, in the picture we saw before, that was basically an unmyelinated axon, right? How's it going to work if we take a look at myelination? How do we spread that message, right? Well, it turns out that we are going to go ahead and rely on those little nodes of Ranvier, those little in-betweens. They're going to be an excellent way for us to communicate with the axon and send down our nerve signal. So here on our illustration, we could see that it says for you a sodium influx at the node will generate an action potential. So you're properly exciting the membrane. The sodium will diffuse along the inside of the axilla to the next node. And when it's doing that, it's actually starting to lose its signal a little bit, but not to worry because there are excitable voltage gates right near this illustration, which will then allow them to activate and thereby continue on with your action potential. So the action potential literally is carried from the bare part to the bare part. Here's what it looks like if we're doing myelinated sheets. Because remember, what we're doing is we're kind of hopping and we're engaging the section of the axon that's unmyelinated. This is called solitary conduction, and as you can see right here, you have a membrane that's excitable in green, and then the way the figure is set up is that you see that a certain section is inducing an action potential, and what's going to happen is instead of just kind of making it this way, it's going to literally look like it hops over to the next spot. And from there, it will hop over to the next node, exposing the axon that's unmyelinated in those particular sections. Now, look what follows the area of excitation, or the area where the action potential occurs. This little yellow area. What's the yellow area representing? A refractory membrane. So this is going to be a part of the time limit that basically will determine how fast the nerve signal can move and how fast a secondary nerve signal can come. because remember, the refractory period is meant for you to kind of slow down, and if it's an absolute refractory period, we are not doing anything. But if we're doing a relative refractory period, we have to induce the stimulus to get the response that we're looking at. Now, one last thing I want to discuss in this chapter is how the synaptic connections between the neurons can be used as a way to explain our memory. And it's all due to the fact that the more you use your neurons, the more synaptic connections they make with each other. Well, actually, it's pretty much throughout our lifetime. But when we are young, you have an extreme amount of synaptic plasticity, which means that your synapses are very willing to learn and adjust, and it makes it easier for you to retain new information and facts. Unfortunately, as we get older, the plasticity starts to diminish a bit, making it a little bit harder for us to concentrate or to learn new facts. But either way, we know that how the neurons work together with the synaptic connections, we are then able to convert our memories into immediate, short-term, as well as long-term memory. So let's start with immediate memory. Immediate memory basically allows you to follow the flow of the room. It allows you to follow a story that someone's telling you. It allows you to kind of see how the events that you're currently in, you remember the beginning and you remember the end. So for instance, if you're watching an episode of your favorite show, as you're paying attention, you're using your immediate memory to follow the storyline. And this is also one of the reasons why if you are, for instance, listening to a lecture and you're just kind of listening to it, you start off with the immediate memory because you're trying to follow along what I'm saying. But if you kind of stop paying attention for a little bit and maybe you're watching something else or you go to get something to eat and you just let me talk, by the time you come back, I'm on a different topic and you have no idea how I got there because you weren't paying any attention at all. So that immediate memory is really good for us to kind of echo what's going on in our current situation. Now, if you have a fact or a procedure or an event that is memorable enough, quote unquote, we see that it can transition from immediate memory to short-term memory. And short-term memory basically means that we can hold on to this thought for a few hours, where immediate memory is often in just a few seconds. Short-term memory is usually very effective if you're doing a repetitive task. So for instance, if you always leave your keys at the same two locations, if someone were to ask you what your phone number is, you would most likely have to memorize it first. And the way you're going to memorize it is by repeating the numbers in order several times. As you're doing this repetitive step, you're basically increasing the amount of calcium that's in the synaptic knob between the two neurons. And the more calcium you have, the easier it is for you to kind of recover a memory or to remember something later on in life. Now, if you use an event or a memory frequently enough, it will essentially transition from short-term memory to long-term memory. And long-term memory is often described as declarative or procedural because it's very matter-of-fact what you recall and how you can utilize it. So for instance, declarative means that you can remember facts or you can remember text. You remember how it goes. So for instance, I would hope that most of us could tell me the story of, for instance, Snow White. That's a childhood story that most of us have heard. We are, for instance, able to remember our birthday, hopefully our parents' birthday. These are all examples of facts that we're remembering because it's something that we continuously surround ourselves with. Even if you can go ahead and you can tell me about the neuromuscular junction and not looking at your notes, you can tell me things like what are the different components, the acetylcholine receptor, the synaptic knob, the acetylcholine, the synaptic cleft. Sorry, I'm trying to recall all the different parts of the neuromuscular junction. If you are able to sit down with me and explain it to me without looking at your notes, then I will give you a good applause because that means that that knowledge has transitioned from short-term over to long-term. Procedural long-term memory is more like motor skills, so it's things like remembering how to tie a shoelace, how to make a bow, how to ride a bike. These are all kind of like muscle memory entities that will make it easier for us to remember in case we do forget. The long-term memory has more to do with nitric oxide, and that nitric oxide keeps the synaptic connection in a vivacious state, meaning that it doesn't need to continuously to be stimulated, but it does need to be called on from time to time to make sure that it is properly handling what needs to get done. So at the bottom right here, I said physical remodeling of synapses, new branches of axons, or sometimes the dendrites, molecular changes which will allow us to recall these facts long term. And that is because the neuron will go ahead and produce more neurotransmitter receptors, and it will also start releasing nitric oxide. And this will, of course, stimulate the reaction between the presynapse and the actual moving from immediate to short-term to long-term memory. Alrighty. Oh, one thing I want to say to you is that the plasticity of your brain tends to stay nice and fluid as long as you keep challenging yourself. So that's why people tell you things to do things like Sudoku or puzzle or trivia. Basically anything that keeps the mind going and learning new facts helps increase how long the plastic stability will be around. Alrighty, so I do hope that we're able to take the information from chapter 12 and transition it from our immediate memory to our short-term memory to our long-term memory. So when we encounter each other, hopefully a few months, maybe a few years from now, that you'll be able to see me and you'll be able to say, hey, I still remember all the different myelination steps, and I still remember the difference between immediate, short-term, and long-term memory. And this will all come from just repetitive motions. So that's why they tell you to read the book, read your notes, make your notes and read them, do the smart book module, do the homework. And you keep thinking, well, this information is a little bit overload. I see it over and over again. And the reason I do that is so it makes it easier for your memory to go into the long-term category versus the immediate or short-term. Alrighty, so having said that, I am going to go ahead and pause over here. Remember, I'm an email away with for any of your questions, comments, or concern. And we will go ahead and meet next time, and we're going to go ahead and keep talking about the nervous system in chapter 13. Until then.